Let's see how we're doing here. 4 equations with 6 unknowns, right? My 6 unknowns are A, B, oops. My 6 unknowns are A, B, C, D, A prime, and B prime. 6 normalization constants I have to find, but I only get 4 equations. How the hell am I gonna do it? Well, let's think about this for a moment, okay? So in a given time sequence, what we're really only interested in solving this problem is forward moving particles. We know that we're going to have a reflected wave here, and eventually if we have some boundary right here, we're also going to have a reflected wave. But in solving this problem, right, for what I'll call forward motion, we can actually eliminate the B prime constant. We can set the B prime constant equals to 0 because I'll remind you that B prime constant, here it is in region 3, right? Because that's attached to the E negative IKX. That's a particle moving in that other direction. So we'll eliminate it. We won't worry about it, okay? Well, then what about the other left moving particles? Is that important? As it turns out, it is. These reflected waves, right, where I get a reflected wave going back the other way, or a reflected wave going back this way, those are important because they fix the probability of this particle moving in the opposite direction. So we can't ignore those. But we'll ignore, right, the particle that's reflecting all the way back here because the tunneling has already occurred, okay? So so now we've got 5 unknowns with 4 equations. How do we specify a 5th equation? Because with 5 unknowns, we're going to need 5 equations, okay? Well, we can talk about this in terms of transmission probability. What's the probability that the particle will make it through, okay? And so I'll reflect that with the letter T right here. And the probability that the particle is going to make it through, we can relate to the normalization constant in this region to the normalization constant in this region. So in other words, those normalization constants are really giving us the amplitude of these waves, okay? And so if we can see now that the particle has made it through here, and there's some finite amplitude on this side, and some finite amplitude on this side, then we know that this probability is going to, or this transmission probability is going to be related to the square modulus. I'm going to do my cool little Dirac notation. It's going to be related to the square modulus of a particle moving this way in region 1. So I'll put a little 1 right there, over the wave function square modulus of a particle moving the same direction in region 3, okay? So that now gives us a 5th equation where we're going to say the transmission probability is going to be equal to the square of this A constant over the square of the A prime constant. And thus we have a 5th equation with 5 unknowns. And then all we have to do now to normalize this, we don't have to go through and do psi squared set equal to 1. We can just normalize all of these things to each other by solving a 5x5 system of equations, okay? We can do that with matrices. We can do that with Mathematica. There's a number of ways that we can solve a system of 5 equations with 5 unknowns. And that's how we normalize this tunneling problem. Okay, so that's been going on for a while. I do have just a little bit more to carry on related to this transmission probability. So I'll pick that up in a second part of this lecture. Okay, folks.